Hi, this is part 5 of Getting Started with KA9Q Radio. In this episode, we'll look at a headless Linux server using Ubuntu and running on that KA9Q radio and KA9Q web. That allows the server to provide over the local area network an HTTP web connection, and we'll demonstrate a wideband spectrum from the RX888 receiver. And this will allow us to do this without actually streaming the wideband samples over the local area network. So in this episode, we'll look at sometimes problems we may have with booting a headless PC. We'll look how to edit and reconfigure Grub, how to edit our server so that it can boot into a CLI or command line interface only mode, or it can boot into a GUI mode. There's some resource consumption differences between those two. We can use Renmina on Ubuntu to remotely log into the GUI, and we'll use SSH if we want to log into the CLI. And then a few pros and cons of running KA9Q web server on the same PC as KA9Q radio and running a client and where that client goes. So it's possible to run KA9Q radio and KA9Q web on a headless server. By headless server, we mean one that does not have a monitor, a keyboard, or a mouse plugged into the computer. It's just a computer with power and a local area network connection, and in our case, a USB connection to an RX888 receiver. Headless servers give us the opportunity to have a low-powered, small form factor server that can be remotely located so that we can access it from a client in a different location. Some of the problems we sometimes run into on a headless server is that some Linux PC computers won't actually boot when headless. Normally, this isn't a problem with a Raspberry Pi because it generally will boot headlessly without a monitor, keyboard, or mouse. The headless PC can provide a KA9Q web page service, and we'll look at that a little later in the demonstration. Some of the boot problems when trying to boot Linux headlessly usually are due to either the boot needs a monitor or it needs a keyboard. In the case of not having a monitor and the PC requiring it, we can generally use a $3.50 dummy HDMI plug, sometimes called a ghost display plug, that we can plug into the HDMI output of the computer, making it think that we have a monitor attached. In my particular case, my PC would not boot without a keyboard. Without a keyboard, the computer detects a string of random characters, and unfortunately that halts the Grub boot sequence. A couple of alternatives is that we can plug in a real keyboard. We don't actually need to press any keys on the keyboard. We just need to plug one in to avoid emitting random characters. Another possibility is to use a micro Arduino. And for example, Seed Studio has one that's $4.99. And the Arduino keyboard library will allow us to emulate a real keyboard. This particular device is very low power and can be powered from the USB. And so in that case, we can tape a small device to the computer and get away from not being able to boot without a keyboard. Some other boot workarounds, we can use an IP KVM device. That stands for Keyboard Video Mouse, that runs over Ethernet. And so it provides the keyboard emulation, video capture, and a mouse over IP. This kind of device can send keyboard keystrokes to the PC. It can send mouse keystrokes to the PC, and it will capture the output of the HDMI and send it back over the Ethernet so that we can essentially remotely control the server even without having any physical presence there. The Jet KVM, for example, which is a Kickstarter project, is currently kickstarting at about $69. There's another alternative if the PC will boot completely headlessly, and that is we can use Renmina, which is a program available on Ubuntu, which will give us similar control of a remote GUI where we can log in and run the PC remotely as though we were there. Additionally, a number of server motherboards include IP-KVM functionality integrated in. One of these is called IPMI for Integrated Platform Management Interface. That's, for example, available on Supermicro servers. Dell servers have their own version of that. It does a similar function, allowing the server to be accessed over Ethernet and providing equivalent functionality. That web interface is just a little bit different. With no key press, we need to configure grub so that Linux boot is the default or the first entry in the grub menu. One very convenient tool is called grub-customizer, and you can install that in a recent version of Ubuntu. And then if you do have the server set up to enable GUI login, you can use grub-customizer to set the boot order and the devices that will boot, the timeouts, etc. If you have a CLI-only server, then you can configure grub using grub-edit-env. You cannot use a text editor, even though it's a text file. You have to use grub-edit-env, and then on Ubuntu, for example, you'll want to edit /boot/grub/grub-env. Once you're done with that edit, then you need to use sudo update-grub because the text editor is not does not provide the capability to do this outside of these tools. Ubuntu and Debian, even with a full GUI installed, can be configured to boot into either GUI or CLI-only mode. GUI mode is very convenient for initial setups and configuration. The GUI tools are very easy and intuitive to use. But having the GUI boot available, even if you're not using the GUI and it's just sitting at a login screen, does consume a fair amount of resources. The server that we'll be demonstrating here is a 6-core, 12-thread Core i5 11500 series Intel processor. I made a few measurements with the KA9Q radio software running. And with the GUI available but just not being used, HTOP reported a load average of 0.92. When the GUI is shut down so only a CLI boot is available, the HTOP load average was about 0.52. On a 6-core processor, that equates to a CPU load average for the GUI available but not utilized of about 15.3%, and in the CLI-only mode of about 9.3%. You need to divide the HTOP load average by the number of cores available. Even if the server is in a CLI-only headless mode, it can still serve a web page, for example, KA9Q Web, to a remote client web browser. And later on in the example that we'll show, the server is configured into a CLI-only mode, so it doesn't actually have a GUI boot, although the GUI tools are actually installed. To set the boot mode, the first thing is you should make sure that SSH is enabled on boot. So you should set sudo system control enable SSH. If that's not enabled, you won't be able to log into the server in a CLI-only mode. If you have a keyboard, monitor, and mouse on the server, you can use that locally to enable SSH. And in this case, the server has had that enabled so that when it boots up, we'll be able to get into the headless server that isn't using a GUI with the SSH tool. System control allows you to determine how the system will boot in the future. To set the GUI plus CLI mode, you use system sudo system control set dash default graphical dot target. To set the CLI only mode, sudo system control set dash default multi dash user dot target. And you can change these at any time so that future boots will come up in a GUI mode or a CLI mode. And this, of course, assumes that you actually installed a GUI onto the server. The GUI access to a headless server can be done using Renmina, which is a program available in the more recent versions of Ubuntu Linux. For Ubuntu, I found this requires 24.04 on the server and greater than or equal to 22.04 on the client. So the server has to be running in CLI mode and providing a CLI boot if you want to use Renmina to get into the graphical boot mode. On the server, using the GUI and a local keyboard and mouse and display, go into Settings, Sharing, and Remote Desktop, and then you'll need to enable Remote Desktop and enable Remote Control. To use Renmina to log in GUI to the server, use RDP mode and then tell it the IP address, the login username on the server, the username's login password, not the one assigned by Renmina, but the one that you use to log into Ubuntu on the server. And if you're going to use a GUI with RDP, I recommend setting your firewall to block RDP access from the internet to prevent potential security issues from having a wide open server. KA9Q Web, which we've been using in this series, is installed as it was in the previous videos on the server, and KA9Q Web can be set up as in the previous videos. There are two versions of KA9Q Web available now. Franco Venturi's original, which we discussed in previous episodes, and Scott Newell N5TNL has forked that and added a bunch of really cool new features. His is available on github.com/ScottNewell/KA9Q Web. For this demonstration, I've installed Scott's version and we'll be using that for the demonstration. So this is a block diagram of what we're going to do in this episode. We have a headless Linux PC, and in this case, it's been set up and the GUI interface turned off after it's been configured. It has an RX888 plugged into it. There's a BIOS T to an active wideband loop. On the server, we're going to launch KA9Q-radio in the CLI in a bash shell, leaving that bash shell open. And then in a separate SSH bash shell, KA9Q-web will be launched. Then over on a PC that has a browser with SSH terminals, we'll use those SSH terminals to get into the server. And then after radio and web are up and running, we'll then launch the browser and navigate to KA9Q Web's web interface, which is on the IP address of the server, :8081, which is the port that it uses. So our PC has a display keyboard and mouse, but our Linux server in this case is headless, and we're getting to it using just the CLI interface. So next we'll go into the demonstration of setting that up. Where should we install KA9Q Web? If we install it on the client, it requires roughly 600 kilobits per second of multicast traffic from the server to the client. So this would be an example where we have KA9Q radio running on the headless server and using multicast to stream the wideband spectrum display samples over to the client over our local network. If KA9Q Web is installed on the server, then we don't need to multicast that traffic over our network. We access the wideband spectral display using HTTP on our local network, and that's significantly reduced bandwidth on the network. The client can still separately access samples from KA9Q radio if we've set up various demodulators on it. But we can also demodulate baseband audio using the wideband spectrum display client if we choose to. On the server, we open an SSH window, Radio D, and after opening an SSH window, we invoke Radio D at rx888-web.conf. So we first open an SSH window, then which provides us a bash shell, and then we invoke the Radio D daemon. On the server, we'll open the additional SSH window, change to the KA9Q web directory, and then we'll run KA9Q web-m, and we have to give it the status channel name of KA9Q-web, and leave both the SSH windows open so that we can note any error messages. And on the client, we'll open a browser and navigate to the server IP address :8081. In this demonstration, the server has been booted up. It's in the CLI only mode, so it doesn't actually have a GUI to log into. What we're going to do is on the client, open two SSH windows. The first one, we'll go into KA9Q Radio and start up Radio D with the web configuration file. Then in the second window, we'll go into the KA9Q web directory and start the web program. Then finally on the client, we'll open a web browser to the server port 8081, where we'll be able to look at the wideband spectral display. So here we'll open a window and SSH into the server. Now we'll change to the KA9Q radio directory. And bring up the program. And now KA9Q radio is running. We'll bring up another window and we'll SSH into the server. And we'll change into the KA9Q web directory. And from here, we'll invoke the web program. And now we'll bring up the browser. Port 8081. And here we can see the wideband spectral display that's being computed on the server and then HTTP across the network to the client display device. This is the N5TNL version. It's got a lot of nice features on it. We have a max hold button. We can change back to the normal. We can change the display range as may be useful. We can set the frequency range that we might want to display. And so there's a lot of interesting capabilities. Recent versions of KA9Q radio need a new library called libogg-dev to be installed and then rebuilt. And Scott Newell's fork needs to be rebuilt against recent versions of KA9Q radio because there was one function that has a parameter change in KA9Q radio. We also need to make sure the status and data channels have different names on the server. In the file radiod at rx888-web.conf, there's a definition for the status channel and one for the data channel. They need to have different names. I've chosen to use status is equal to webctrl.local, and the data channel to be data equals web.local. Then we invoke, in this case, KA9Q-web -m, and the status channel name would be webctrl.local. So, a summary of the typical options. If our Linux server has a CLI-only access, then we'll get to it using SSH. We need to know its Ethernet address, or we need to access it via Ethernet, knowing its IP address and knowing the user that we wish to log into. So SSH requires username at the IP address, and then we'll provide it the password. If we have a GUI on our Linux server, we have a couple of options. We can use a IPKVM device to log in, which is also IPMI if it's built into our server, or we can use a web browser using Renmina RDP, and there we'll tell it the IP address of the device, and we'll also use the Ethernet interface to do that. This is a look at the stock rx888-web.conf file provided in KA9Q-web/conf config, which has several config files. And in red, you can see on the fourth line of the file, we edited the status to give it a different name than the data name. And in this case, we have TTL equal to 0, and that prevents the raw data from KA9Q radio from being multicast outside of the host. The software sources, as in previous episodes, are KA9Q radio from Phil Karn's GitHub page. And again, there's a new dependency that was recently added. KA9Q web, there are two sources, Franco Venturi's GitHub site or Scott Newell's fork of that. It will need to install the Onion web library on the server if we run KA9Q web on the server, as we're doing in this demonstration. I'd like to thank John Melton for the C code for visualizing the spectra and integration with the Onion libraries, Franco Venturi, who adopted that code to KA9Q web, Scott Newell, who's forked Franco's repository and added some really cool new features, HamSci project, which is kind of where we're using a lot of this, and Tapper, who provides project support and has started to provide accessories for the RX88 receiver, which are very convenient.